Hi everybody. In this lecture we are going to discuss about sampling and reconstruction. So we have studied in this course about digital signal processing, but the real world signals are analog. They are not digital. Then how do we use all these digital signal processing concepts like designing the filters, etc., digital filters in the real world scenario? So the answer is that we take the real world signals, we sample them. Sampling basically means converting the signal, the analog signal or the continuous time signal into discrete time or digital version, and then processing it and reconstructing. So it is like this. We have a sensor. The sensor could be some some measurement device which is measuring the real world analog whatever we are measuring, like temperature, pressure, or the vibrations, the sound vibrations, anything. So for example, a microphone is a sensor which is measuring what I am speaking. When I speak, the membrane of my microphone vibrates, and this signal goes to A to D converter. So it means I convert it into digital version, analog to digital conversion. And then this digital signal I process using my DSP concepts, whatever I have learned. And then I again convert it back into analog. I convert my digital signal back into analog signal. Okay, I have to these plots are there. So A to D conversion happens like this. And then I process it, maybe low pass filtering, high pass filtering, etc., whatever I want to do. And then I convert the digital signal into an analog signal by interpolating, for example. And then the actuator plays, for example, it is a speaker which is playing the audio. Yeah, so what is sampling in time domain? Time domain means I have a signal, GAT, let's say it's an analog signal, that's why GAT. It's an analog signal. For example, when I speak, my speech makes the microphone membrane vibrate, and this vibration is connected with a transducer which generates a voltage, a small voltage, and that voltage level is my analog signal, GAT. Then I sample that signal at a sampling rate Fs, sampling frequency Fs, and capital T is my sampling time, or omega t is 2 pi upon capital T, basically the frequency in radians per second. Now I can represent my time as nt, right, because n is an integer and capital T is the sampling time. And so how do I obtain my discrete time signal? GNT is simply GA of NT. So this is the meaning of sampling in the time domain, right? I convert my signal GAT to G of N. Now, what does that mean in the frequency domain? How does my frequency spectrum change when I sample? So let's say GAT is my time domain signal. Let's assume that it has a Fourier transform. It's a continuous time Fourier transform. GA j omega. This is capital omega, which is for continuous time frequency. So GA j omega is the continuous time Fourier transform of my GAT, my analog signal. And for GN, the transform is DTFT, discrete time Fourier transform, G of e to the power j omega. Now the question is, in the frequency domain, how do they relate? So what is the relationship between G A j omega and G e to the power j omega? Right, so to answer this question, we have to take a long journey. Let's start that. So let's see how my signal changes. So my G of n is simply, we can call that G of n is GAT multiplied by periodic pulses, right? Let's say this is my GAT, and I multiply it with periodic pulses. And now what is PT? PT is basically summation over delta t minus n capital T. Capital T is the gap between the two consecutive pulses. the pulse train. Now this delta is not a Kronecker delta function, but a Dirac delta function. Dirac delta means you integrate over it and you will get 1. Right? The integral over one peak is 1. But the value here is kind of not defined, tends to infinity. So this is my pulse train. So basically, what is the meaning of sampling? I have my continuous time signal and I multiply it with the pulse train. And what does this lead to? This leads to a discretized version of my continuous time signal. Let us call it as GPT. So what is GPT? Basically GAT multiplied by this pulse train. So let us write the expression for GPT. My GPT is equal to GAT multiplied by the pulse train. Now, what is pulse train? PT is simply summation over all the n from minus infinity to plus infinity, delta t minus n capital T, right? We have seen this formula before. Now let's, P stands for pulse here, right? So this is the pulse, this is the modulated pulse train. Basically, this is what contains all the information which I have in my discrete time signal. This is the analog counterpart. Now, what we are interested in is the Fourier transform of GPT, right? So that is the direction we are heading to. How do we derive the Fourier transform? That's why we are doing all this simplification. Let's plug in the value of PT here and we get this form. Now what is this equal to? This is, I can take it inside my summation, and you know that delta multiplied with something and then integrated, or this simply becomes GA n capital T, right? So let's look at the spectrum now. So what is my GP j omega? What is the Fourier transform of my pulsated signal, or the analog signal which is multiplied with the pulse train? So let's plug in the values which we just derived for GPT. It's simply the multiplication of GA nt and delta n, delta t minus nt, summation over all n, though the pulse train multiplied with my analog signal. Now this Fourier transform is linear function, right? And this is a constant because this is n capital T. There is no small t term here, so it's a constant with respect to small t, right? So I take my f inside because of the linearity property of Fourier transform, and I get this. Now the question is, what is the Fourier transform of delta t? If I know this, then computing this is very easy. So let's see what is the Fourier transform of delta t minus nt. So just apply the formula of continuous time Fourier transform, and it is very simple to see that it is e to the power minus j capital omega n capital T, right? And let us plug in this value in our equation. So this is what we get. So this is my Fourier transform, the continuous time Fourier transform of my analog signal multiplied with the pulse train. Now ultimately I'm not interested in this. I'm interested in g e to the power j omega. So what is g e to the power j omega? It is simply g n e to the minus j omega n. You already know that. Now compare these two things. What do you get? If you compare, you find that my g e to the power j omega is simply gp j omega, and you are considering not the continuous omega or continuous time omega, but the discrete time frequency omega. Basically, if you replace this capital omega times capital T, you get small omega, right? So if I want to study this, it is good enough to study this because of this relationship. So that's the whole idea. So let's zoom out. So what are we trying to do? We are trying to see if I know my GA of j omega, what is the relationship with my g e to the power j omega, right? So, and we found a relationship between g and gp. So, but let's further go to see how does it relate to GA j omega. So a little bit of more work. Let's start with the basic equation that this is the basic relationship, right? We know the Fourier transform of this, this and this. Now we want to find the relationship. So let's plug in the values. What is PT? PT is the pulse train, right? And we can write a pulse train in this form. How? By using something called continuous time Fourier series. Okay, these are some equations. This is the general equation of continuous time Fourier series. If you have done the course EE301A, then you would have read this. So basically, this is the continuous time Fourier series, and you see here PT is simply delta function, and therefore this is 1 upon capital T. So, and PT, you know, this is the inverse of basically the how do you represent the Fourier series. This is the Fourier series, and these are the coefficients of Fourier series. This all stuff comes from E200 Fourier analysis. So you don't have to worry about it too much if you are able to understand this equation. So now GPT, let's plug in the values here, back here. So this is what we get. Now, what does that mean? If I take the Fourier transform of the whole thing, we want to know the relationship between this and this, the Fourier transform. So let's take the Fourier transform. So what we get this. So basically, it's multiplication with a phase term, and the multiplication with phase in the time domain, it brings about a shift in the frequency domain. That's what we get here. So this is the relationship which we were looking for between GA and GP, GA and GP. Now, once you know GP, you know how to compute G e to the power j omega, right? Simply replacing the omega will do the job. So this is small detail, just the same thing that we read, that if GA corresponds to GA, then multiplication with the phase term brings about a shift in the frequency term. So that you already know. Okay, now this is all good. It relates GP and GA in the omega, basically continuous time Fourier transform, but we are interested in the discrete time Fourier transform, and we know this relation. So using that relation, we can very easily plug in the value of capital omega in terms of small omega, and we get this relation. So this is essentially the relation between the DTFT of the discrete time signal and GA of j omega, which is basically the continuous time Fourier transform of my original analog signal. So the Fourier transform of analog signal, Fourier transform of the discrete signal, how they relate, the relationship is here. And let's look geometrically at it, what it means. So let's say this is my GA j omega. This is the analog signal Fourier transform, continuous time Fourier transform. And what happens in this formula, it is just copies repeated at omega equal to k times 2 pi, right? When omega is k times 2 pi, then this same pattern repeats. K is an integer, right? So basically, this was my original analog thing, and if I look at the DTFT, it is simply copies of the same thing. So that's simply the relationship. So, and also you remember that if you sample in the time domain, you get periodic copies in the frequency domain, and that's what we just now proved. Very simple. Now, what is the physical interpretation? So you imagine you have GAT, the analog signal, the continuous time Fourier transform is GA j omega. Let's plot it something like this. So it has non-zero values between minus omega m to plus omega m. Now you multiply it with the periodic pulse train, which has a Fourier transform of p j omega, and we have already seen that this is the Fourier transform of the pulse train, and it comes out to be something of this form, which is basically this, right? So basically this term, whenever omega is 2 pi upon capital T or multiple of that, then the whole thing will become summation of 1, 1, 1. So it's a large term. Otherwise, it cancels out. So now this term is 2 pi upon capital T is omega t, right? So what we see here is this is the Fourier transform of p j omega. So basically this whole exercise was there to compute this p j omega, and this is how it looks like. Now when I know that my GPT is simply GAT times PT, the product. So what do you mean when you have product in the time domain? What do you get in the frequency domain? It is simply convolution, right? In the frequency domain, it's simply the convolution. So that's what you get. GP j omega is like this. And what is GP? What is G e to the power j omega? The DFT. That is simply you convert your continuous frequency into discrete frequency by dividing it with capital T. That's it. So this is the physical interpretation which we have seen. So basically your small omega is simply, if you multiply capital omega t with capital T, what do you get? You get 2 pi, right? So you get 2 pi. So that's why your period becomes 2 pi. So 0 to 2 pi, and that is your period in the discrete time Fourier transform. Now, what is the concept of aliasing? So imagine that your signal is band limited, which means the analog signal has values or non-zero values between capital omega m, minus capital omega m and plus capital omega m. And this is your pulse train, and you convolve the two, you get GP j omega, basically the periodic version. And how does it look like? It looks like this, the periodic copies, right? Now imagine if your sampling sampling frequency is small. Sampling frequency is small means they are closer, right? The peaks in the omega are closer. Then what will happen if you convolve the two? There will be overlaps. And so that is the problem. If omega t sampling frequency is small, which means sampling time is large, you are very lazy in sampling things, then you get aliasing, which means protruding tails. So the tail of this signal will go into the other copy, and then they mix inseparably, and you can't separate them out later. So the signal gets distorted, or signal gets you lose the purity of the signal. Now that is where we get the sampling theorem. Aliasing can be avoided. How to avoid aliasing? So if we ensure that this omega t minus omega m is the maximum frequency for which my Fourier transform is non-zero, right? Means my Fourier transform is limited in this range. Then what I get is that if omega t minus omega m, this value is larger than this value, then there is no aliasing, right? Very obvious. And so basically if this condition is satisfied, then there is no aliasing. And rearranging the thing, you get omega t, or sampling rate, should be more than twice the maximum frequency present in your signal. So if your maximum frequency present in your signal is 1000 hertz, then you make sure that your sampling rate is more than 1000 hertz, for example. And this rate is called the Nyquist rate. It's an important number. It's a Nyquist rate. Means your sampling frequency should always be greater than the Nyquist rate if you want to ensure that things are not distorted. Your signal is not distorted because of sampling. You're not losing any information because of sampling. And but the real signals may not be band limited. Means their tails may be so long that no matter whatever large sampling rate if you take, but still the tails will protrude into the next copy. So what is the solution? The solution is remove those tails by using a low pass filter. By using a low pass filter, you limit your signal to a certain range only. Let's say I'm interested only in up to 1000 hertz signal, or let's say in speech I'm interested only in up to 3000 hertz signal. For example, when earlier days the telephones were there, they wanted to minimize the amount of information sent over the channels so that they can send information very quickly. So to minimize the information, to minimize the amount of data sent, minimize the data size, they band limited the speech signal, and they band limited it to, let's say, 3000 hertz. So first they have to do low pass filtering to remove all of the frequency components, and then do sampling at that rate, and then they can ensure, okay, that the tails are not protruding into the next copies. So when we do the sampling. So this is how we do the sampling, and then so you do the sampling and you do the DSP on the digital signal which you have obtained, and now you have to reconstruct it back to analog so that you can play it with your speakers, or you can do the real world stuff in analog domain. So what is reconstruction? Let's see an intuitive understanding of it. In the frequency domain, what you have to do is remove the copies, just keep the central copy, right? And in the time domain, it means you interpolate the impulses intelligently, means interpolate the pulses. So let's see it pictorially. What does it mean? In the time domain, you have Gn. From Gn, you will obtain an estimate of GPT. GPT is the periodic pulse train multiplied with Gn, or your signal, modulated pulse train, you can say. GPT hat, because this is an estimate of the original modulated pulse train. And from here, if you do an interpolation, you can reconstruct GA hat T. So this is the estimated original signal. You can compare it with the original signal, and then you can check whether there is some distortion or not. If you have followed some good practices like Nyquist rate, etc., or anti-aliasing, then you can control the distortion. Now, what does it mean in the frequency domain? You have your G e to the power j omega, which is the DFT of or DTFT of your continuous time signal, discrete time signal, and then from G e to the power j omega, you have to construct GP j omega, which is the continuous time thing. Like this thing will correspond to this, and now you want to pick the central band using a low pass filter so that you can remove the copies. So removing the copies in the frequency domain will lead to making the signal continuous, and that's what you get. So your GA hat j omega is simply one copy, and you remove the other copies, right? So this is all about sampling and reconstruction. The overall picture is something like this. You have some sensors, you want to convert it into digital signal, and you do some DSP, convert it back to analog, and then use the actuator to do whatever you want to do in the real world. Now I open it up. So what I wrote earlier as simply A to D conversion, it has many steps, 3 steps you can see here. First, you have to do anti-aliasing filtering by removing the extra tails which may protrude into the copies. And then you have to do sampling, so sample and hold. And hold means basically you hold the same value in the continuous domain. And then you convert it into the digital by actual sampling using a DAC card or something like that. And then you do the DSP, digital signal processing, on your discrete time signal or digital signal. This may also include quantization if you want to do DSP, digital signal processing, otherwise discrete signal processing. And then you convert it to continuous domain. Basically, you obtain your GPT, right? GPT or GPT hat. And then you do the reconstruction filter, where you actually do the interpolation, or basically using a low pass filter to convert your GPT hat into GAT hat. And then this GAT hat goes into your actuator and you get your desired result. Thank you very much.